Now, let's look at this zero-sum two-player games in the context of game theory. And in that, primarily, we would focus on the different kinds of strategies. How do we identify the domination strategy? What do we typically mean by Minimax criteria? And also, I would focus for some time on trying to explain about the randomization strategy. Again, we'll try to understand these various strategies along with the different terminologies that are used in the process to get a good hold on this zero-sum two-player games, right? Now, whenever I talk about this zero-sum, as the word itself is saying, whatever is the gain to one player is coming purely from the loss to the other. So they are not like win-win kind of games. When one player is winning, it is at the cost, at the loss of the other player. So the players are always in conflict for winning, because whatever is won by the one player is always the loss of the other player. Now here, the whole process is about choosing different kinds of strategies. And as a part of the game theory, some of the main assumptions that lie are any player, while he is choosing his own strategy, does not know the strategy of the other. So he is choosing his strategy. He will not know what his opponent is going to play. That's one thing that comes up. Along with that, there is another important thing. Once a player has chosen his strategy, he will not change his strategy. So these two things are the guiding points or the assumptions which drive the game theory. And in this, when I talk about the different kinds of games or the different classification of games, it is purely based on the number of strategies that are available to each one. If let's say player A and B are playing, A is having two strategies from which he can choose. B is having three strategies from which he can choose. We call those kind of games as a 2 by 3 game, because A has two options to choose from, B has three options to choose from. But in general, we are talking about the games where the finite number of options are present. So we'll try to represent one game and we'll try to see how the strategies are typically picked up and how the representation goes. Let's say I talk about two players, A and B. And let's talk about A is having two strategies, whereas B can take three strategies. Right? A is having two strategies, B is having three strategies. Now, what is that I can say? A strategies, let's say I talk about 1 and 2 with Roman numerals. B strategies, let me talk about 1, 2, 3 with regular. So the representation typically goes as the payoff when A follows 1 and B follows 1. A follows 1 and B follows 2. A follows first strategy, B follows third. Here I say A follows second strategy, B first strategy. A follows second, B second. A follows third A follows second and B the third. Now this is a typical representation of any game. any game gets its representation in the form of a matrix. And whatever are the entries that went into the matrix, we call them as payoffs. And the payoff is read like this. The way you read the payoff is whatever is the number that is there, it is the loss to player A, which would be typically the gain to player B. Right? Whatever is the loss to player A. So we'll represent a number that says that whatever is the number that is shown, that's actually the loss to player A, and the same number is the gain to player B. That's a typical representation. Right? If I put a number 3, it means A has lost $3 and B has gained $3. So that is how we represent that particular matrix. When A is choosing the first strategy, B is also choosing the first strategy. The loss is $3 to A, and the same is a gain to B. And the main intention of this entire game theory is to come out with optimum strategies. What is the strategy that A has to follow? What is the strategy that B has to follow in such a way that it becomes more and more profitable to them? So if the particular strategy has to be more profitable to A, what is that he has to choose? And if it has to be more profitable to B, what is that he has to choose? And finally, can I come out with the value of the game as such? Can I compute the overall value of the game? This is what the entire intention behind the development of the game theory exercise. Now here we have a few interesting things to really look at and evaluate. One we call as the principle of domination. For that, let me try to take one simple example to explain. I'll take a simple 3 by 4 game, right? Let me take a simple 3 by 4 game, means A is having 3 strategies, whereas B is having, sorry, I'll take a 4 by 3 game. A is having 4 strategies, B is having 3 strategies, right? So A can actually follow either 1, 2, 3, or 4 strategies. B can follow 1, 2, or 3. Now I'm writing the payoffs here, right? Probably let me write the payoff 3, 2, 5, 1, 3, 2, 2, 3, 4, and 5, 4, 3. Let's say these are the payoffs for this game. Now here is where probably it's like it's reading of this is like this. If A has chosen strategy number 2 and B has chosen strategy number 2, the loss of $3 is for A and the gain of $3 is there for B. That's the meaning of this kind of a representation. Now, here when I say one strategy, either A strategy or B strategy, one strategy is dominating the other, is a dominating strategy compared to the other if the choice of this strategy is at least as good as the other one or better than the other. Good or better, right? Equally good or better than that when I compare it with the others. So from players A's perspective, in all cases, that particular strategy should result in minimization of the losses, should have lesser losses compared to the other strategy, because A strategy is always to minimize the losses, because whatever we see under the A scenario, we look at it as the loss amount. So the intention is to minimize the losses. But when I look at from player B's perspective, my intention always is to maximize the profit. Now, what I have to really see is if there is any strategy of A which is resulting in the minimum loss in all the cases, irrespective of what B takes, it should result in a minimum loss compared to the other strategy. Then we call those kind of strategies as the dominant strategy, and that particular strategy that is getting dominated can very well be removed. Now, let's try to understand in this case. Probably look at the strategy number 2 versus 4 of A. Now, what is that you are seeing? Okay, here the loss is 1, whereas it is 5. So, this is lesser. Here the loss is 3. Here it is 4, lesser. Here the loss is 2. Here the loss is 3. So, irrespective of whatever B chooses, I see that if A chooses strategy number 2 compared to strategy number 4, he can very well minimize his loss, which means 2 is a dominant strategy here. 2 is a dominant strategy, whereas 4 is a dominated strategy. Right? Now, whichever is dominated can very well be removed, which means this particular column can totally be removed. Right? Now, what will happen to my updated matrix now? There are only 3 strategies for A and 3 strategies for B. So this becomes 3, 2, 1, 1, 3, 2, 2, 3, 4. So now, is there any more dominating strategies? Now look at it from B's standpoint, right? If I'm looking at from B's standpoint, I really need to see, is there any other strategy for B which is always resulting in a maximization compared to that of A? Now probably 3, 2, 5, sorry, this is 5. Okay, now look at the comparison between this first strategy of B and third strategy of B. Now, third strategy is always having a higher profit compared to the first strategy. In all the cases, the third strategy is having a higher profit compared to the first, which means the third strategy is a dominating and the first is a dominant strategy, and I can very well remove off the first. Now, this entire game reduces to 3 strategies for A, but there are only 2 strategies for B, becoming 2, 3, 3, 5, 2, 4. Now again, now compare this strategy versus this strategy of A. Again, I could see that strategy number 2 is minimizing the losses in all the cases compared to strategy number 4. The strategy number 2 is minimizing the losses in all the cases compared to strategy number 4, which means strategy number 3. So strategy number 3 can very well be eliminated. So I am left with only strategy 1 and 2 for A and strategy 2 and 3 for B. The overall matrix results in 2, 3, 5, 2. Now this is what again I have to see, is there any kind of a dominant strategy? Now here, because of the dominant strategies that are present in this whole flow, a 4 by 3 matrix finally got reduced to a 2 by 2 matrix. Means there are 2 choices that are available for A and 2 choices that are available for B. Now out of which one A will choose, which one B will choose? we have to really come out with a mechanism, right? In some cases there is an easy way to choose. In some cases it's not an easy way to choose. But the first step in the identification process is identify these kind of domination strategies, right? All right. Now we'll move on to the next important concept in the same, which is the minimax criteria. Now that we have identified the dominating strategies, right, and removed the dominant ones, now I'm using this minimax criteria to finally arrive at what is the strategy that is optimal to choose. What is that optimum strategy for A and what is that optimum strategy for B? And this is done simply through a minimax criteria. Now what do we do here? Let me try to take an example again. We'll talk about a 3 by 3 game wherein we are talking about the three choices that are available to A and three choices that are available to B. And the payoffs are like this: 7, 3, 3, 5, 4, 6, minus 2, 2, 0. Now here there may not be any kind of a dominating strategies. I assume that I have removed all the dominating strategies, right? Now here I really want to go ahead and apply the minimax criteria. Now let's try to apply the minimax criteria from the player A's standpoint. Now the intention here is minimize the maximum loss. Minimax is nothing but minimize the maximum loss, and maximin when I am using it is the maximize the minimum gain, right? Now if I really have to see what it means, okay, let's see from this game. If player A is choosing the strategy 1, what is the maximum loss that he can get? The worst case scenario he can get into, he can get a loss of 7, right? If A is choosing strategy 1, his loss is going to be 7. If A has chosen strategy 2, his loss is maximum loss, the worst case scenario is going to be 4. And if he is choosing strategy 3, his worst case is going to be 6. So what the minimax criteria says is, okay, these are the maximum losses in each of the three. So you choose that strategy which minimizes the maximum loss. So choose this strategy number 2 because that is the one that minimizes your maximum loss. So from the A standpoint, using this minimax criteria, from the A's standpoint, the strategy that he is going to choose is strategy number 2. Strategy number 2 will be chosen by player A. Now, when I look at it from player B's perspective, I am more interested in seeing at the maxi min. Whatever is the minimum gain that he is going to get, he has to choose the maximum out of it. So if he is choosing strategy number 1, the minimum gain is 3. Whereas if he is going with strategy number 2, the minimum gain is 4. A strategy number 3, the minimum gain is minus 2. Now, again, he has to maximize the minimum gain. Again, this one. So even the player B will choose a strategy number 2. So when player A is choosing strategy number 2, player B is choosing strategy number 2, this particular intersection point, which is a value 4, which is what is the intersection point here, that is what we are calling it as the equilibrium point. That is what is an equilibrium point. This strategies, they are in equilibrium. These two strategies are in equilibrium. And if you see in a very simpler way, this particular 4, this particular 4 is largest in the column. If you look at a quick way, it is the largest in the column along with the smallest in the row. That is what will give us the equilibrium point. A quick way to observe out is, I'll see, okay, the largest in the column is this, but this is not the least in the row. So this can't be an equilibrium point. The largest in this column is this, but this is also the least in the row. So this is an equilibrium. The largest in this column is this, but this is not the least in the row. So this is not an equilibrium point. So I can very well check out for the point the largest in the column, the least in the row. If some such thing exists, we call that as an equilibrium point, and a better definition for that in the game theory language is also called as a saddle point. A saddle point is existing means there is a strategy, there is a pair of strategy for both A and B, which both of them can take, which will maximize the gain for B and minimize the losses. So using the Minimax criteria, the strategy that both of them can choose has been provided. That is what we call as the saddle point, and the game would be in the equilibrium position like this. But there could be a few games where there may not be any kind of saddle points. Here the game is quite clear. There is a saddle point, and that saddle point should be the typical criteria which both A and B to choose to really maximize their profit. And in this case, we also say that the value of the game is $4. I can very well say that the value of the game is $4, right? Now, what if there is no saddle point that comes up? This is where we are going to get into the randomization strategies. In cases where any kind of saddle point does not exist. So for that, let's quickly take a simple example to understand. Let me take a simple case where A has two strategies to play, B has two strategies to play. Again, the payoffs are plus 8, minus 5, 2 and 6. Let's say these are the payoffs in each of the cases. Now, I know that, okay, this is the largest in this column, this is the largest, but this is not the minimum in the row. So this can't be a saddle point. Here this is the largest, but this is not the minimum in the row, so this cannot be a saddle point. This is the minimum in the row, but this is not the maximum in the column, so this is not the saddle. So I really, for this kind of an example, don't have any kind of a saddle point. Now, if I don't have a saddle point, there is no one fixed strategy for me to go ahead. This is where I really look at a randomization kind of a strategy, wherein, okay, let me look at like this. Here, on a random basis, I'll choose the strategy. But for just understanding how we use this randomized strategy, I will try to see it's purely probability based, right? The choice of this strategy is purely probability based, wherein we here the intention is to minimize the maximum expected loss. Now, let's say A will choose let's say a probability P. A will have a probability P of choosing option 1 and some 1 minus P of choosing option 2. right? A has a probability of P of choosing option 1 and 1 minus P of choosing option 2. Now let me assume that B will choose 1. If B chooses 1, what is the expected payoff, payoff or expected loss for A? So he will have a loss of 8 with a probability P, and a loss of minus 5 or a gain of 5 with a probability 1 minus P, which would be like 8P minus 5 plus 5P, otherwise 13P minus 5. Now in case B chooses option number 2, what would be the loss for A in that case? He has a loss of 2 with a probability of P, and he has a loss of 6 with a probability of 1 minus P. So it is becoming 2P plus 6 minus 6P. So it is becoming 6 minus 4P. So in case B is choosing 1, his loss is 13P minus 5. In case B is choosing 2, his loss is 6 minus 4P. In either of the cases, this loss should be minimum. Right? In either of these cases, this loss should be minimum. So, and we can see that one is an increasing function and the other one is a decreasing function. So what we can simply see is that the minimum can occur when these two strategies, when I'm equating these two. 13P minus 5 is equal to 6 minus 4P, resulting in 17P equal to 11 and P equal to 11 by 17. Resulting in P equal to 11 by 17, which means this is the probability that he should choose option number 1, and he has to choose option number 2 with the probability of 6 by 17, so that his overall loss is going to be the minimum most possible. And if he chooses this way, what is going to be his loss in this case? His loss is going to be 13P minus 5, which is 13 into 11 by 17 minus 5, probably 143 minus 85 by 17, which works out to some 58 by 17. Right? Around 3 point something is the loss that can come out, which will work out to be the value of the game. Now let's try out seeing if the same thing from the B standpoint. Now let me assume that B will choose option number strategy number 1 with a probability of Q and strategy number 2 with a probability 1 minus Q. Now if A has chosen the strategy 1, now B's gain is what? 8Q, right? If A has chosen 1 already, so B will make a gain with a probability of Q, and he'll make a gain of 2 with a probability of 1 minus Q. So 8Q minus 2Q, 6Q plus 2 is the gain which B is going to make if A chooses 1. If A chooses 2, B is going to make a a gain of minus 5 with a probability of Q, and a gain of 6 with a probability of 1 minus Q, resulting in 6 minus 11Q. Now again, these are the gains. Now he has to get the maximum possible gain. Now that can occur when both of them are equal. 6Q plus 2 is equal to 6 minus 11Q, resulting in Q is 4 by 17. So he has to choose a strategy of 1 with a probability of 4 by 17 and the second strategy with a probability of 13 by 17, which would typically result in What is the gain if you see 8 times? What is the probability? What is the gain he is going to get? 6q plus 2. So 6 into 4, 24 by 17 plus 2, which will again work out to 58 by 17, which means in either of the cases, the gain of one is same as the loss of the other. So that can very comfortably be talked of as the value of the gain. Now, in short, if there is no saddle point, if there is no equilibrium point, the strategies need to be chosen by A and B in such a way that A will have to choose strategy number 1 with a probability of 11 by 17 and strategy number 2 with a probability of 6 by 17, while B will choose strategy number 1 with a probability of 4 by 17 and strategy number 2 with a probability of 13 by 17. This is the mechanism how we go ahead with respect to the randomization strategies in case there is no saddle point existing, right? So that's what we would like to look at from the perspective of zero-sum two-player games. Initially, we looked at the domination strategies and then removed them using the, and after that we worked on the minimax criteria and then the randomization strategies, right?